All right, so finishing up a couple of applications from worksheet 13B. We're going to be using our calculator. It's going to be in parametric mode and also in degree mode. So if you want to go ahead and change your modes, you might want to do that now. But we're going to need to write some functions before we can investigate the graph. And they give you some clues here. So initial velocity of 28 feet per second. So that's this initial velocity, and it does measure in feet, which means when I'm using the formula gravity coefficient there, we're going to use the negative 16. The angle with the horizon, or with the ground, would be 56 degrees. It's not like the literal ground. When you guys throw a ball, they measure from like a parallel ground surface. So that's the theta. And then the initial height that is released is 4, so that's h sub naught. And they want me to answer some questions about how far away will the ball land and how much time until the ball lands. Now this second question we could have answered like with our Algebra 2 skills, but this first question we're going to need to use our parametric skills. So in parametric mode, I think your formula, is it like 8x1 and y1? Okay. So when you're in parametric mode on your calculator, you need to program your functions. For the horizontal component, remember the formula from yesterday, starts with t, which is like their x variable, but t is the parameter for the parametric mode. And then initial velocity, which is 28. And then it's times the cosine of the angle, so cosine 56. And then for the vertical component, because it's measured in feet, we have negative 16 t squared plus, and I always write the t first because I tend to forget it. So t times initial velocity, 28, times the sine of 56. And then plus the initial height of 4. So we're going to get those programmed into our calculator. All right, so everything's typed in. We're in parametric mode. I'm going to double check that I am in degree mode. Some of us had this problem yesterday where we were in radian mode still and it wasn't graphing right. And they want us to answer some questions. So a few things we can do here. Let's first look at the graph. So if you would please go to window, and she's throwing a ball. And I don't know anything about this Julie, but I don't know if she's got like a Hulk arm or whatever, but I feel like she's not going to throw the ball for that long. Baseball players, how many seconds? Is 5 okay? Okay. Now for t-step. If we're going to look at a graph and you want it smooth as possible, just do the 10th of a second, so 0.1. X is measuring horizontal distance. I already have some answers from me doing this previously. 50 is going to be plenty horizontal. 30 okay for Y? Oh, for X? I can even pull back to 30? Okay. Y is good at 20. So she does not have a Hulk arm. That's good. All right, so if we hit graph, that's a beautiful picture. So the question says, how far away will the ball land? You have a couple of options. You can hit trace, and you can start scooting around until you see where it hits the ground. Whoops, I went too far. Right about there. So I'm not going to get a real accurate answer, but you need to answer carefully, guys. Which one of these components measures the how far away part of the question? That's the X. So the ball hits the ground about 25 feet away from her. You could say 25 point something if you want, but about 25 feet is a good answer for me. And then how much time until it lands? So for that, do you notice there's a T component up there? So how long was it in the air before it hit the ground? About 1.6 seconds. And again, these are all approximated answers. Nothing's real exact here. Okay? The other place you could have looked was at your table. But my table right now is counting by seconds, so it's not giving me a whole lot of information. So if I want to look at a table in parametric function applications, you're going to want to change, obviously 0 is a good time start. You're going to want to change your time to count by something smaller than 1 second. So like, again, 1/10 of a second would be appropriate. So if you're a table reader, and this is where you like to get your information from, you're going to have to change the parameter counting by, instead of integers, by tenths. So keep that in mind. You good? Can we move on to the next part of the lesson? Good. Find worksheet 14. Anyone have any problems on their homework last night that they're willing to admit? Yes? You got problems on the homework too? Okay, let me look at the homework before we get to the lesson. I just got confused. I get confused every day. You're in good company. All right. Which one, what gave you problems? Okay. Okay. Gotcha. So they want you to eliminate, right, rectangular form and graph the equation. I think they want you to graph this new equation you're getting, is their intention. But it should be the same as if you graph the parametric, if that makes any sense. Did I even bother to graph mine? Oh, I didn't. What a lazy bum. Oh. That's probably why you were confused. You're like, you didn't graph it. What do I not know? You didn't know that I was this lazy is what you didn't know. And then which one? Number 33? Okay, I just wrote an answer of yes. That's very helpful, isn't it? Okay, Del Mar attempts a 43-yard field goal. He kicks the ball at 41-degree angle with initial speed of 70. Goalpost is 15 feet high. Okay, so that is an excellent question and a really good one to get ready for what you'll see on your test. The goalpost is 15 feet high. Is the kick long enough to make the field goal? So what you have to do, first we got to set them up, right? And you're going to want to graph this. So that same formula we just got done using, we'll use that same sort of formula. So t times the initial velocity, which was 70, times the cosine of the angle, so cosine of 41. And then this is measured in feet, so negative 16 t squared plus t times 70 times the sine of 41. And then this is just a normal field goal, right? So they're saying, I know it's technically not on the ground, but let's pretend it's on the ground. So you can put a 0 back there if you want, but nothing. So you're going to graph it. And it says a 43-yard field goal. So the distance here has to be to 43. And I don't know exactly what it looks like, but something like this. What you're going to have to do, Anna, is you're going to have to figure out how high up the ball is when it's 43 feet out. So you can just use that trace feature. And then if your ball is higher than 15 feet, that means it'll go above the goalpost and it'll make it. Or you could just watch and wait. Some kids like to answer that a little differently. I feel like the graphing and the tracing is the easiest way to do that. Okay. So your question here is, does it hit 15? Or is it above 15, I guess is the question. Apparently the answer is yes, according to my really stellar, thorough key of yes. I know, it's so helpful when I write things like that. Anything else on the homework mess with you? Oh, well, excused. All right, so the second day of parametrics. It's going to start off with a review question of what we did yesterday, which I am totally willing to do. Was anybody gone yesterday? All right. Well, let's take a look at this one. I'm actually not going to do this whole question because as I look over here, I go, wow, that's a lot of points I'm going to plot. And you guys know how I feel about plotting points. But what you would have to do is, obviously your calculator's already in parametric mode. You'd enter your x and y. You would either physically restrict yourself to only look at t from -3 to 1. So -3, -2, -1, 0, and 1. Or you could set up your table to start at -3, but remember we just messed with the table to count by tenths of a second. So you'd have to go back and mess with it again to count by integers. So since I know you guys are going to do this part fine, are you okay if I just tell you what the ordered pairs are? So this is 8, -1. This is 3, 1. This is 0, 3. This is -1, 5. This is 0, 7. Now, I had a conversation with someone yesterday where like they were having some calculator trouble, and I said, you know, you can really come up with these ordered pairs without the calculator. It's not that hard. -3, you're going to plug it in for t into both the x and the y, and then you're going to get two numbers. It's just using the calculator obviously is less work and it's easier, so that's why we're using the calculator. So the endpoints specifically are the beginning and ending points, so this guy and this guy. So you're going to write 8, -1, and 0, 7. So let's talk about window used. Now the t is a gimme window. They literally told you what to use for t. So t goes from -3 to 1. And then for x's and y's, you guys should be able to look at your data results and tell me where we should look for x's and y's. So the x's don't go any smaller than -1, and they don't go any higher than 8. So if you want a window where it kind of extends beyond your limits, I'm going to go, how about like -2 to 9. You can go further than that. You don't want to have your endpoints on the edge of your window. It gets kind of weird. And then for y's, they go as low as -1 and as high as 7. So I'm going to go -2 to 8. So you can mess with that window a little bit. It doesn't have to be that exact window. The next part is the annoying part. It's the graphing one. So you do have to graph the ordered pairs. So 8, -1, 3, 1, 0, 3, -1, 5, I can't read, okay, and 0, 7. Oh my gosh. I screwed that up right at the end. Okay, that was supposed to be curvy. That didn't work. Now, notice endpoints, endpoints. They don't have arrows continuing off the edge. This is not a continual curve that goes on forever. But what other thing am I going to have to add to this picture to indicate orientation? Those weird little arrows. So just show me that it goes like this. And that's what the graph looks like. It's pretty lame. But one of the things you had to do quite a bit on your homework is write it in rectangular forms. This is where you look at your two parametric equations. And which one do you solve for t? Which one do you manipulate so you solve for t? The x one. We're going to solve for t. Now this is kind of weird because there's a squared on it. So you're going to start by adding the 1 over. And then you would have square rooted it, right? But in math, when you square root an equation, isn't it both positive and negative of whatever that root is typically? Now in functions this gets kind of weird. But because we have parametric equations right now, just go ahead and put down plus and minus, and we'll talk about whether we need it or not in a second. So now this value, we're going to plug in for t, but into the other equation, into the y equals equation. So rectangular form is just your regular graphing form. Y equals 2 times, instead of t plus 5, we're going to write this. So I think this is a case where I do need to keep the plus or minus. But I'm not going to write it here because this is like the world's weirdest place to write a plus or minus. Most humans would write it out in front. So plus and minus 2 times the square root of x plus 1 plus 5. So on those book assignments when it said write it in rectangular form and then graph the function or graph the equation, they would then want me to go graph this guy. Do you guys remember what a square root graph looks like? It's one of those weird side bends. So if you have a positive and negative square root graph, don't you have like a sideways parabola? Okay, now specifically this sideways parabola is shifted left 1 and up 5. Yeah. Isn't that what we graphed? Now you notice your parametric equation doesn't continue on and make that full weird sideways parabola shape because it had restrictions, right? The x's and y's were restricted. Did the directions in the book on that question say to do something with the window? Yes, and state any restrictions on the domain. So those questions, those 9, 11, and 13 in the book, they don't want you to go to town and graph an entire parabola. They're going to want you to just graph the part that's according to that parametric. So you would have restricted, well, I'll be honest, Anna, that question. Don't you think it's kind of easier just to graph the stinking parametric to begin with? Yeah, me too. So the restriction you guys could find, because it's a restriction based on t. Remember how they gave you this t restriction right off the bat? You would then have to say, okay, well, if t can't be any smaller than -3, figure out that endpoint, and then same thing with 1, figure out that endpoint, and that's where you restrict your domain. It's very annoying, in my opinion, to do it that way. So I guess the benefit to doing parametric equations in that form is you don't have to do all that work. All right, this is new. What if I give you this question? This is from your book. This is not in your notes, I don't think. So we have x equals 2 cosine theta and y equals 4 sine theta. And I want you to write those in rectangular form. Clearly, these are parametric equations. They're incorporating sine and cosine. They're just a little simpler looking than like our Luigi question, which had velocity in it. So what they've done is they solved for the cosine function, and then they solved for the sine function. So like here, they divided both sides by 2, and they wrote it as x over 2 equals cosine. That's what you, whoops, wrong color. That's what you see right here. And then same thing here, they divided by 4, and they said sine of theta equals y over 4. Now, think to yourself, why would I possibly want to do that? Well, we're going to come back to an old friend. Remember this guy? That's a Pythagorean identity. That is just a true statement from trig. It's been proven for many, many, many millennia now, where cosine squared plus sine squared equals 1. So what they're going to do then is instead of saying cosine, remember, cosine of theta is the same thing as x over 2 in this problem. So they plug that in for cosine. They plug in y over 4 for sine. And then they squared the fractions. So that's how they're getting x squared over 4 plus y squared over 16 equals 1. Wait a minute. What is that? Isn't that an ellipse? So we're going to be bringing back conics today. Good thing we just got done doing them. All right, so if I made you graph this, rather than graphing this mess in the parametric form, I'm pretty sure we could graph an ellipse with our eyes closed. Not really, that'd be weird. Where's the center of this ellipse? 0, 0. And then be careful, remember ellipse can reverse order, so the major axes and the minor axes, they're not necessarily like first or second. So you just have to watch which direction you're traveling. So like for instance, pen, you could work any day now. That'd be good. In the x direction, that axis is a length of how many units? Be careful, this is b squared, so it's 2 units, right? So you're moving 2 units to the right and 2 units to the left. And then for the major axes, it's moving in the y direction. That would be a 4 unit. So up 4 and down 4. And then everybody's favorite moment when I try to draw an ellipse. That was almost good. Looks a little bit like a potato. That's okay. All right. So let's look at what you have on your notes. You've got a question like this. Exact same directions, very similar inspired question. So you're going to start by solving for sine. So you're going to divide by 3, and you're going to write down for me that the sine of theta is x over 3. You're going to do something similar over here. You're going to solve for cosine. So divide by 2, and you're going to write down for me that the cosine of theta is y over 2. This is important to me. This is important to me because sine squared plus cosine squared equals 1. Isn't that the identity? So instead of saying sine squared, let's call it x over 3 squared. And then instead of saying cosine squared, let's call it y over 2 squared. All right, just a little bit of simplifying and then we're done. Squaring fractions, you can square the numerator and denominator separately. So this is x squared over 9. This is y squared over 4 equals 1. We know that's an ellipse. If they wanted me to graph it, I sure could, but good news, they didn't ask you to graph it. So you get to walk away from that question. That's not bad, right? And I know some of you are looking at that like, well, I never would have thought to solve for cosine and use an identity. I know, that's why we teach you the lesson. So now you know. Now you know what to do. All right, let's take a look at, I'm going to skip 2 because it's really the same thing. It's quite boring. Let's move on to number 3. Did you know that you could graph inverses in parametrics? Sure, why not? What's the main rule about inverse functions? Like, what's the whole premise of an inverse function besides that they undo each other? Say it again. Elaborate on that thought. You might be heading in the right direction, but I'm just like how do you find an inverse function? Let's go way bare bones, guys. You flip the x and y, right? That's the premise of an inverse function. Your inputs and outputs switch. Now, because they switch, a lot of things happen. Domain and range switch. The symmetry of it will switch over the line y equals x. A lot of things happened. One undoes the other mathematically. But think about what you just said. The x's and y's switch. So when you look at a parametric equation set, if I'm trying to graph his inverse, and you guys told me the x's and y's switch, here's what we're going to do. On our calculator, we're going to graph x1 to be 3t minus 1, and y1 to be t squared plus t. And then underneath it, I don't know if you noticed this, but you have multiple parametric options, just like how you always have y1, y2, y3. Well, there's a bunch of other guys. So for x2 and y2, shouldn't we just kind of switch these around? Because that's the whole premise of inverses. They switch. So t squared plus t for x, and 3t minus 1 for y. All right, I'm going to pause the video for a moment so I can get these typed in. All right, so we have our original parametric function in x1 and y1, and then we have what we think is the inverse in x2 and y2. And we're going to graph them. And remember, one of the properties of inverse functions is they were reflections of each other off the y equals x line. So you should see this really cool symmetry across that diagonal identity function. Right now, I don't really know what the graph's going to look like because who knows what I did to my window in the last question. So what you might want to think about doing is maybe adjusting the window yourself. The other option, which I think it tells you here, use negative 10 to 10 for t. Okay, cool. And then it says do a zoom square. So zoom square is not one we use too often, but zoom 5. Oh, well, that's beautiful. Is that what you got? Okay. So the identity function, the y equals x line, would kind of split right through the middle here. And you would see that inverse symmetry that we're looking for on inverse functions. Cool beans. Was that really impressive to you? Yeah, me neither. Let's move on. All right, to the back. Oh. There's some interesting applications on this part of the notes. So to model a ball that was thrown straight up into the air with an initial velocity of 90 feet per second. Yes, ma'am. Not working. All right, so back to this one. We are throwing a ball straight up with an initial velocity of 90 feet per second, starting at a height of 5 feet. So they're giving you some parametrics to graph, and then they want you to turn on the bouncy ball for fun. Okay. Will do. Here's what we're going to do. Put this into x1, put this into y1. And then they want this into x2 and y2. Now, while we're typing all that in, they also want you to kind of mess with. Do you remember how we did yesterday? We changed it to a ball instead of just drawing a curve. Let's try the other one. See if you like that one better. Okay. You guys weren't very impressed, if I recall. You were like, yes, this is not something I care about. I understand. It's okay. All right. 8. Sorry, I should have paused the video so y'all didn't have to watch me type slowly. Okay, if you could, back on your first parametric, if you want to have fun with how it's graphing, go back to this option. You can change whatever color you want, but remember how if we go to the right, we have some options. I'm actually going to choose the second one this time. This is just going to be like a bouncy ball. Well, they say it's a bouncy ball, but It's not going to bounce. There are functions where it would bounce. It would have this periodic, you know, boom, boom, boom. This isn't one of those. So I'm going to choose that one. You guys don't have to if you don't want to. I think we have to adjust the window though, huh? So go to window. Let's see what weird stuff happens to us now. For t, they want you to go 0 to 6. And then I'm going to leave it counting as tenths of a second. And then for x's, I want us to go 0 to 10. Oops. And then for y's, they want -10 to 200. Let's see if all this work was worth it. I think the answer is probably no. That's okay though, let's try. Did you see it? It did bounce. Was it worth it? Yes, that was the highlight of your morning, I bet. Should we do it again? I think you have to quit and then go grab. Oh, I have to read. Oh, I have to like change the function? Okay. Okay. Watch closely. It's going to happen. It's going to go fast. You know what bothers me about that? It doesn't simultaneously graph it. I'm sorry, TI, you're going to need to fix that. Because if I'm going to have the bouncy ball go, and I'm going to have the parabola that measures like horizontal and vertical distance, I want it like simultaneously graphing. Otherwise, I'm not impressed. Sorry. I'm never going to do that again. Sorry. It's pretty harsh. Okay, let's move on. Oh, this ladybug question's kind of cute. We are going to skip it, though. Sorry. The bouncy ball took up all of our time. So, a ladybug, they end up having you graph it, and like you literally see this little ladybug like marching back and well, it's not a ladybug, it's a dot, but it marches back and forth. It's the bouncy ball again. He's very useful, that bouncy ball option. I'm gonna skip that one. I'm sorry. Does that really bother you? You really wanted the ladybug one? Okay, you stay after class. We'll do the ladybug one. All right, let's talk about rocketry. That sounds scary. So remember these functions? They're back. Let's do a couple more. There are several of these on your homework. I think something I didn't make a big deal about yesterday, and I kind of wish I had. This component, this -1/2 g, that's the gravity constant times -1/2. So like we know from my Algebra 2 experience in feet per second, it's actually -32 feet per second is gravity's acceleration. But because of this formula needing a 1/2 coefficient, that's why it comes out to -16 per feet per second squared. And then, I always get the numbers wrong. James, help me. Is it 9.8 meters per second? -9.8 meters per second squared. But if we throw that 1/2 in there, you'll notice on your formula sheet, the coefficient is a 4.9 because that half is built into that formula. I didn't make a big deal about that yesterday, and I wish I had. Either way, you guys don't need to stress about that because it's on your formula sheet. And on your test, we're very much American here at Harlem for some reason. Like we keep giving you feet per second squared questions. So -16 is the coefficient you're going to be using. So this question, Manuel launches a toy rocket from ground level. Cool. Initial velocity of 80 feet per second. That's this guy. And then, yeah. Why do you think I use the same number? That's confusing. All right, 80 degrees is the angle. They want me to write the parametric equations. Okay, so we actually did this yesterday and we warmed up with it today, so let's see it again. So we're going to type, I always do t first, so t times the initial velocity of 80 times the cosine of your angle, which is also 80. And then for your y parameter, or y equation, it's measured in feet, right? So -16 t squared plus t times 80 for the velocity times the sine of 80 degrees. And then I could say plus 0 because it's from ground level, but I'm not going to bother writing that down. So let's get this typed in. All right, so we have our parametric equations typed in. And as far as window goes, what are we doing? We're launching a rocket. Oh boy. I mean, I really don't know anything about rockets. I think we need to go big. So bigger than 6 seconds. Maybe. I don't know. Way bigger? 7. I don't know. Maybe not that big for time, actually. Let's try, like... I'm just going to go 20. That might be too much. I don't know. But for, like, horizontal distance, I have some answers written down, so... I'm thinking, like, you have to go past 50. 100's okay? Alright, we'll go with that. I mean, sometimes it's like, by the time you figure out a good window, if you just would have guessed, like, a kind of good window, you would have been done, so... And for y min, I keep putting it at 0. I kind of like to go negative, because if it's going to be a hit the ground question, I kind of like to have a little wiggle room underneath it. So, I don't know, let's see what happens. Oh, doesn't like something. What did I do? I put something stupid. Yes, I did. Good call. Alright, now graph. Oh! Dang it! My rocket disappeared. Alright, so remember how I had that setting? And this is why I shouldn't use the bouncy ball, because I forget to change it back. Well, that wasn't very exciting. There we go. Okay, that works for me. So first question, how long will it take the rocket to travel 10 feet horizontally? You can either go on your tracing of your curve, or you can go on the table. I'm just going to trace on the curve because I'm lazy and I'm running out of time. So trace, and I want to know 10 feet horizontal, so I should be watching the x to see when it hits 10. Oh, too far. Right about there. So the question is, how long will it take? And your answer should be, I mean, about 0.7 seconds. You can, I think I wrote down 0.8 on mine, because it's somewhere in between 0.7 and 0.8 apparently. And then what will be the vertical distance at that point? So about that. This is all very approximate, isn't it? And then what is the maximum height reached? So you're going to have to scroll over to the maximum. You can't use your calc menu here. It's not going to work for parametrics. So you have to kind of estimate where you think the peak is reached. And the question is, what is the height? So which one of those represents the height? Yeah, the 97-ish height, yeah. So about 97 feet. And then the next question is, how far away does it land? Well, I don't know. I gotta go find it. So keep scrolling. So the question was, how far away is it? Your answer to that would be which component? The x, right? So it's between 68 and 69 feet. So something about that. So as far as your homework for tonight, you have a little book assignment continuing on that same set of pages. And it's going to be a lot of those, well, it's not a lot of anything. It's a very short assignment. It's those trig questions where you had to magically use sine squared plus cosine squared equals 1. So it's like a bunch of those, and then they want you to throw down an ellipse on each of them. So little review of ellipse graphing. They're all centered at 0, 0 though, so they're pretty easy to graph. And I think there's an application question that you're assigned. I think it's number 40. And I kind of gave you a little heads up on the window on the key. So if you're having trouble setting up your window yourself, you can take a peek at that, okay? All right, good luck.